Okay, so in this problem, we're looking for the influence line for the shear at C, and C is here. So we know eventually that we're probably going to have to cut the structure there to find that shear. So I'll just emphasize that by drawing a nice big line. And tell me, what free body do you want to look at? Do you want to look at the one on the left or the one on the right? Yeah, it doesn't really matter that much, but I'll use the one on the left. Now, if I do that, I need to know what? Reaction at A. So we're going to have to actually find the influence line for the reaction at A first before we can find the influence line for C. So let's do that real quick. So I'll draw the free body diagram for this, and I'll assume that I have AY, BY, and then we'll have our unit load at some distance x, and this whole distance is 12. So how do I find AY? Some moments about B. So let's do that. So I will sum moments about B, make sure it's in equilibrium. When I do that, my unit load is going to create what kind of moment, positive or negative about B? What's this moment arm? Yeah, it'll be 12, the total distance minus x. So that means I'm going to start off with 1 times 12 minus x. That's the moment of the unit load. And then AY creates what kind of moment about B? Negative. And it has a moment arm of 12. So it looks like AY is going to be 12 minus x divided by 12.
Why is it minus x, right, when you first got to 12 minus x? That.
Why is this 12 minus x?
Yes.
Well, the total length is 12, and this distance is x. So to get this distance, you have to take the total minus x. Plus, if you add the two together, what do you get? 12. So this will be good for any x value. Now, even though the problem doesn't require it, let's go ahead and just plot the influence line for AY as a function here. So when x is 0, what do we get? 1. When x is 12, what do we get? 0. So there's my influence line for the reaction at A. Okay? So now I want to go back and cut it at C, look at the left body, and see what we get. So this will be when the unit load is on the structure, so that'll be between 0 and 3. And I'll have a free body diagram that looks something like this. I'll have my reaction, AY, which is this. I'm going to write this a little different. This is just 1 minus x over 12. I can get away with writing one less number. Same idea. That's my reaction at A. I'm looking for the shear at C. That's positive shear. And what else do I have? Well, my unit load is between 0 and 3, so it's got to be on the structure at some position x. And this part is 3 feet. Now, all I'm looking for is shear, so how can I find shear? Sum the forces in the y direction, so I'll do that. So I'll assume up for positive, and I'll sum forces in the y direction. So starting over here, I've got 1 minus x over 12, that's AY acting up. Then minus 1, that's the unit load down, and then minus CY. I'm sorry, shear at C. So let's solve for the shear at C. And it looks like I just get minus x over 12. Okay?
One second.
Cool? Algebra. Fantastic. I'm reading a book about Leonardo da Vinci, and as smart as he was, algebra to him was a mystery. He could never figure it out. He could barely count. But he could draw. He had a great eye, but mathematically he was terrible. He tried to solve problems by drawing circles. Like if you want to square something, he would try to do it like with geometry. He couldn't figure it. He couldn't get the idea of a variable and stuff like that. It just completely blew his mind. All right, so now let's do the part from 3 to 12. Now remember, unlike our previous study where this would tell you the range of the cut, this is not. This is the position of the load. We're still using the same free body. That hasn't changed. We decided to use the left side, which is 3 feet long, has an A reaction of 1 minus x over 12, has a positive shear at C here, and then it has the unit load at some position x. But now in this one, it's not there because it's existing between 3 and 12, and this is not between 3 and 12. This is between 0 and 3. So it's on the other body over here, which we're not considering.
Why?
So now you just sum forces in the y direction again.
The load is from 3 to 12.
This is the position of the load. Remember, what's the definition of influence line? You're finding your quantity at a point as what moves in x? The load. This is the position of the load. So in this first case, the load is anywhere it wants to be between 0 and 3. In this case, it's anywhere it wants to be between 3 and 12. Well, where's 3 and 12? Not on this body. I think you just encountered what Leonardo felt when he tried to figure out algebra. It's like, what? But it's really that simple. Don't overthink it. This is the position of the unit load. We've already decided to cut the structure at C. Why? Because the problem asks us to. And then we decided to work the left side or the right side. We decided to work the left side. That's it. You're locked into that. Now the only thing that's going to vary is the unit load there or is it not there? That's it. In this case, it is not there. So when I sum forces in the y direction, make sure I have equilibrium. What do I have? I've got my reaction, which is 1 minus x over 12. And what else? Minus the shear at C. So my shear at C is equal to 1 minus x over 12. So to complete the problem, all I have to do is plot these two equations. This equation is valid for what range of x? 0 to 3. And this one is valid for what range of x? 3 to 12. So let's do that. So here's the ordinate value is the shear at C. That's the specific point that I'm interested in. Here is my x. That's 12, and I'll just bring this down. That's 3. So from 0 to 3, I plot this. So when x is equal to 0, I get 0. When x is equal to 3, I get 3/12, which is minus 1/4. When I come to this equation, I plug in 3. What do I get? I get 3/4. I plug in x equal 12, and what do I get? 0. So it's usually customary to connect those. So there's your influence line for the shear at C. So when Mr. Santana is running around his unicycle anywhere from 0 to 3, he's creating negative shear at C. But once he rides past C, and he's anywhere to the right, he's creating positive shear.
At 12, it would be 1.
No. 12 over 12 is 1. 1 minus 1 is 0.
Yeah.
Hey, Dr. Kent,
Yeah.
what causes it to go back up to 3/4? I mean, I know we have the equation.
Well, I'm glad you brought that up. If we look at that particular value right there, what's the change in shear there? Ooh, what's the value of our load? 1. That's always going to be true. As you go from one side of the point to the other, the shear will change exactly the amount of load. In fact, we can use that to our advantage later. So keep that in mind. Put that in your brain and keep it there. What do you think of that? That's pretty cool, huh? Yeah, I dig this stuff. Okay, let's stop. I'm sorry, any other questions?